All right, so let's move on to this is going to be section what? This is section 4.3, and this is called Gauss-Jordan Elimination. And this is going to be a general method for us to, let me just write down what the idea is. This will give us a general, an A, systematic or algorithmic method of solving. That's not a G, that's a G. Systems, linear systems with, more than two variables and more than two equations. Okay, but we're going to need to introduce an idea called reduced row echelon form or reduced form, and let me remind us what the different sorts of forms that we came up with when we were just dealing with two variables and two equations. So two variables, two equations, and when we were dealing with an augmented matrix, our augmented matrices, we were able to transform into one of three sorts of scenarios using row operations. We could have something that looked like this, or we could have something that looked like this. Right. P M 0 1 0 0 0. Or we could have something that looked like this. 1 P M 0 0. Let me just write a 1 here for now, because we could always divide a bottom row if this is something non-zero by this element to make it a 1. Now whenever we were in this case, we had one solution, and we could just read it off. The first variable is equal to m, the second variable is equal to n. In this case, we had infinitely many solutions. It's a watt. That is a watt. That's not a y. That's close to a y. Solutions. It's my abbreviation for solutions. And when we were here, we had no solutions. Why? Well, here, the first variable is n, the second is n. Okay. Here, the bottom equation doesn't tell us anything, whereas the top just gives us a relationship between the first two variables, so we're on a line. The last one says, well, 0 is equal to 1. That's not true, so that's just not possible. But what I'd really like us to notice is this. Each of these systems has the following. Every single row is either all zeros or begins with a 1. The first non-zero entry is a 1. So here we have a 1 and a 1. Here we have a 1, and then all zeros. Here we have a 1, and then a 1 down here. And anything before the first one is a 0. Also, below or above any 1 is a 0. In fact, over here, I could reduce this to having a 0 up here. So let me write that. So anytime we have a 1, anything above it or below it is a 0. Also, any 1 is to the right of any 1 above it. So this one down here is to the right of this one up here. This one down here is to the right of this one up here. Okay. This, and finally these zeros are at the bottom. This is reduced form. Let me generally discuss what reduced form is. So this is reduced, and sometimes we also call it reduced row echelon form. Echelon is a fancy word for diagonal, A matrix is in reduced row echelon form if the following are true. Number one, all rows that have only zeros are at the bottom. They're below all rows that have some non-zeros. So, okay, number two. The leftmost non-zero entry in any non-zero row, any row that has a non-zero entry, is 1. 3. All entries above a leftmost 1 are above and below a leftmost 1 are 0. And 4, all leftmost 1s are to the right of all leftmost 1s above them. And so let me illustrate really what this means with a bunch of matrices. Now what this means is, well, the following are reduced. For example, we've already seen cases that look like this. Okay. Both of these rows are non-zero, so great. Each of them starts with a 1. The entries below or above each one are 0, and this one appears to the right of this one. The one above it is to the left of this one. The one below this is to the right. So that is reduced. How about a bigger one? I drew something like this in class. Again, we see that the first entry in each row here is a 1. Anything above or below a 1 is 0. And each 1 is to the right of any one above it. This 1 is to the right of this guy and this guy. This 1 is to the right of this guy. Okay, great. Let's look at some cases where we actually have some 0 rows. Let's look at 1, 0, 0, 1, 0, 0, 5, 2, 1. Let me even put a 0 here. So here we actually have a 0 row. It appears below everybody else. These two rows, which are non-zero, each have a 1. So the 1 starts. Below and above the 1s, we have 0s. And this 1 appears to the right of this one because it's below this one. How about another? How about something like 1, 0, 0, 2, 0, 0, 0, 1, 0, 0, 0, 1, and 4, 2, 8, something like that. Now this right here is supposed to be a 0. This is in reduced form because, well, none of these are 0 rows, so I don't have to worry about that. But each of these rows begins with a 1. Below and above every single one is a 0. Additionally, excuse me, this one is to the left of both of these ones, this one is to the left of this one, or this one is to the right of both of these guys, This one is to the right of this guy, so it's in reduced form. And finally, let's do one more. Let's say I have 1, 0, 2, 0, 1, 2, and 0, 0, 0, and let's put 0, 0, 1 here. Now again, there are no rows that have only zeros here. Every single row, the leftmost non-zero entry is a 1. Below and above, all of the 1s are zeros. And this one is to the left of both of these guys. This one is to the left of this one. Great, that's all we need. Notice that these guys can be, I can have, two numbers above each other or below each other, but that happens because these are not the leftmost entries in these rows. I only have to worry about what is in the leftmost entries. So these matrices are all reduced. So think about that. Let's look at matrices that are not reduced and see what we can do to make them reduced. So for example, this guy is not reduced. Why? The top one is to the right of the bottom one. That's not the way we want it. We want the bottom one to be to the right of the top one. How can I fix that? Well, if I just swap the two rows, then this guy will be to the left of this guy. So if I swap rows 1 and row 2, I end up with 1, 0, 3, 0, 1, negative 2. Great. I swap the rows. Now this one is to the right, to the left of this one. This one is to the right of this one. How about this example? Let's take 1, 2, negative 2, 0, 0, 1, and then over here 3 and negative 1. What is the problem here? Well, I have a non-zero entry above this leftmost one. This is a leftmost one, and there's a non-zero entry above it. That's a problem. How can I fix that? Well, I want to make this equal to 0. I can add a multiple of this row to this to make that guy disappear. These zeros here are not going to change what's going on over here. To get rid of this 2, I'm going to take 2 times R2 and add that to row 1 and replace row 1 with that. So I get 1, 2, 2 times 1 is 2, so 2 plus negative 2 is 0. 2 times negative 1 is negative 2, so plus 3 is 1. And my bottom row stays the same, 0, 0, 1, negative 1. Great. So now above my 1s, or below my 1s, I have zeros. Everything else is fine. Let's do 2 more examples that make the other conditions not true. Let's say 1, 0, 0, 0, 0, 1, and then 3, 0, 2. What's the problem here? This 0 row is not at the bottom. It needs to be at the bottom. This guy's non-zero, he's at the bottom, this guy's not at the bottom. So we want to put him in the bottom. To fix that, all I have to do is swap the second and the third rows. I just want to put this guy down here. When I do that, I end up with 1, 0, 3, 0, 1, 2, and 0, 0, 0. Okay, that's fixed. Now I've got my zeros at the bottom. One more example of this. Let's suppose I had 1, 0, 0, negative 1, 0, 2, 0, 4, and 0, 0, 1, negative 3. What's the problem here? Well, this leftmost non-zero entry is a 2. It's not a 1. So I want a 1 there. Well, I can just divide this entire row by 2. I can take 1/2 row 2 and replace row 2 with that. And what do I end up with? 1, 0, 0, 0, 1, 0, 0, 0, 1. And the right side becomes negative 1 to negative 3. Check for yourself that this is reduced form, but it is.